A BBC interviewer once asked me, "Why do magnets repel?" Simple question, right? You'd think a physicist could answer it. I've spent my whole life studying how nature works. I understand electromagnetism. I understand magnetic fields. I could write down the equations. But I told him, I can't explain it in terms you'll accept. He looked confused, frustrated even. Here's this famous physicist, Nobel Prize winner, expert on electromagnetism, and he won't answer a simple question about magnets. But the problem wasn't that I didn't know the answer. The problem was the question itself. Why is the most dangerous question in science. It sounds simple, it sounds reasonable, but it's a trap, because what you're really asking when you say why isn't what you think you're asking. You're not asking for an explanation of how magnets work. You're asking me to connect magnetic repulsion to something you already find familiar, something that makes sense to you based on your everyday experience. And I can't do that, because magnetism isn't like anything in your everyday experience. I could tell you that magnetic repulsion is caused by the exchange of virtual photons between electrons. That's true. That's the quantum electrodynamics explanation. But does that satisfy you? No, because now you ask, why do virtual photons cause repulsion? I could go deeper. I could talk about quantum field theory, about gauge symmetry, about the structure of the electromagnetic interaction. But each answer just pushes the question back one level, and you still don't feel satisfied, because you're looking for an answer in terms you already understand. But magnetism isn't reducible to things you already understand. It's fundamental. It's one of the basic forces of nature. At some point, you have to stop asking why and accept that's just how nature works. This interview became famous. People still talk about it. Some thought I was being evasive. Some thought I was being arrogant. Why won't this scientist just explain it simply? But I wasn't being evasive. I was being honest. Why is an impossible question, and today I want to explain why. Let me show you what I mean about why being relative. Imagine I drop a book and it falls to the floor. You ask me, why did the book fall? And I say, because of gravity. The earth pulls on the book with gravitational force. Are you satisfied with that answer? Maybe. It sounds like an explanation. But now imagine you're in ancient Greece. You don't know about gravity. You've never heard of forces acting at a distance. If I tell you the earth pulls on the book, you'd say, what do you mean, pulls? The earth isn't touching the book. How can it pull something it's not touching? And I'd have to explain action at a distance, and you'd ask why forces can act at a distance, and I'd have to explain field theory, and you'd ask why fields exist. Each answer generates a new why. Or imagine I give a different explanation. I say, the book falls because it's seeking its natural place. Heavy things naturally move downward toward the center of the universe. That's actually what Aristotle said. And for 2,000 years, people found that explanation satisfying. It wasn't that they had evidence for it. It's that it connected to concepts they already accepted. Natural places, natural motion, the structure of the cosmos. The explanation felt right because it used familiar ideas. But it was wrong, completely wrong. So what makes an explanation satisfying isn't whether it's true. It's whether it connects to things you already think you understand. And here's the problem. At some point, you run out of more fundamental things. When you ask why about something truly fundamental, there's no deeper level to appeal to. Magnetism is fundamental. Gravity is fundamental. The strong nuclear force is fundamental. The weak nuclear force is fundamental. These are the basic ingredients of nature. They're not made of something simpler. They're not reducible to more familiar phenomena. They just are. And when you ask why about fundamental things, the only honest answer is, that's how nature behaves. We've observed it, we've measured it, we've tested it. That's what we find. Is that satisfying? Not emotionally, no, but it's true. Let me give you another example of how why works differently at different levels. Your child asks, why is the sky blue? You could answer at many levels. Level 1, because that's the color it is. Not very satisfying, but not wrong. Level 2, because of the way sunlight scatters in the atmosphere. Better, but now your child asks, why does sunlight scatter? Level 3, Because air molecules are much smaller than the wavelength of light, and shorter wavelengths scatter more than longer wavelengths. Blue light has a shorter wavelength than red light, so it scatters more. Pretty good explanation. This is what most science books say. But now your child, or you might ask, why do shorter wavelengths scatter more? Level 4. Because the scattering probability depends on the fourth power of the frequency. This comes from the solution to Maxwell's equations for electromagnetic radiation interacting with small particles. Now we're getting technical, but it's still an answer. Level 5. Why do Maxwell's equations take that form? Because of gauge symmetry and the requirement that the theory be Lorentz invariant. Level 6. Why does nature have gauge symmetry? We don't know. It's a feature of how fundamental forces work. See what happened? We went from a simple, everyday question to the deepest levels of physics, and at each level, the question, why, is legitimate. But at each level, the answer is different. At the early levels, we're describing phenomena in terms of other phenomena. At the deeper levels, we're giving mathematical explanations based on fundamental principles. At the deepest level, we reach principles that can't be explained in terms of anything more fundamental. They're just features of reality. And here's the key point. Which level of explanation satisfies you depends on what you already know and accept. If you know about light and wavelengths, the level 3 answer might be enough. If you're a physicist, you might want the level 4 answer. But nobody can go past level 6, because we've reached the fundamental structure of nature. When the BBC interviewer asked why magnets repel, he wanted a level 1 or level 2 answer, something in terms he already understood. But there isn't one. Magnetism is already pretty fundamental. To really explain it, you have to go to level 5 or 6. And at that point, the explanation doesn't feel like an explanation anymore. It feels like equations and abstraction. Here's what most people don't realize. When they ask why, you're not asking for an explanation of how something works. You're asking me to reduce it to something you already find obvious. But what you find obvious is just stuff you've gotten used to. Think about it. Why does pushing something make it move? You think that's obvious. Of course, pushing makes things move. That's just how the world works. But it's not obvious at all. It's just familiar. Newton spent years thinking about this, and his conclusion was radical. Pushing something doesn't make it move. Pushing something makes it accelerate. If nothing pushes it, it keeps moving at constant velocity forever. That's not obvious. That violates everyday intuition. Everything you push eventually stops moving, right? But that's because of friction, because of air resistance. In a frictionless environment, pushing something once would make it keep moving forever. Newton's first law, an object in motion stays in motion unless acted upon, is completely counterintuitive. It took a genius to figure it out. And for 2,000 years before Newton, smart people got it wrong. So when I explain magnetic repulsion by saying virtual photons are exchanged between electrons, you find that unsatisfying. But that's not because it's a bad explanation. It's because you haven't spent years getting familiar with virtual photons. If you had studied quantum field theory for 10 years, that explanation would seem obvious to you. You'd say, oh, of course, virtual photon exchange. That makes sense. But you haven't studied it, so it doesn't connect to anything in your experience, so it doesn't feel like an explanation. The problem isn't the explanation. The problem is the gap between what you already understand and what I'm trying to explain. And for truly fundamental phenomena, that gap is unbridgeable with words alone. Let me go back to the magnet question and really dig into it. The interviewer asks, why do magnets repel? I could say, because they have magnetic fields and like poles repel. But that's not really an explanation. That's just restating the phenomenon in slightly different words. So you push deeper. Yes, but why do like poles repel? I could say, because the magnetic force between like poles is repulsive rather than attractive. Again, that's just restating it, so you push deeper. Why is the force repulsive? Now we're getting somewhere. To answer this properly, I need to talk about quantum electrodynamics. In QED, forces aren't things that just exist. Forces are the result of particle exchange. When two electrons repel, it's because they're exchanging virtual photons. The electron emits a virtual photon. The other electron absorbs it. The momentum transfer from this exchange creates the force. For magnetic repulsion, the story is similar but more complicated. The magnetic field is a manifestation of the electromagnetic interaction. The repulsion comes from the exchange of virtual photons in a configuration that creates repulsive force. Is that clearer? Probably not. Because now you're asking, what's a virtual photon? Why does exchanging them create force? Why does this configuration give repulsion instead of attraction? And to answer those questions, I'd have to teach you quantum field theory. I'd have to explain Feynman diagrams. I'd have to explain gauge bosons and coupling constants and symmetry. I could do it. But it would take months, and at the end, you still might not find it satisfying, because you'd still be asking, but why does nature work this way? And the answer to that is, we don't know. We observe that it does. We can describe it mathematically. We can predict the results of experiments. But we don't know why nature chose these rules instead of other rules. Let me try a different approach. Maybe I could explain magnetic repulsion by analogy. I could say, magnets are like people. Sometimes they attract, sometimes they repel, depending on how they're oriented. But that's not an explanation. That's just poetry. I could say, think of magnetic field lines like rubber bands. When you bring like poles together, the field lines get squeezed and pushed back. That's better. It gives you a mental picture. But it's completely wrong. Field lines aren't real physical objects. They're just a visualization tool. They don't actually push on anything. So now I'm choosing between option 1, give you the correct explanation, virtual photon exchange, quantum field theory, that you won't understand and won't find satisfying. Option 2, give you an incorrect but intuitive explanation, field lines pushing that feels satisfying but is wrong. Option 3, tell you that I can't explain it in terms you'll accept. I chose option 3 because I'm not going to lie to you, and I'm not going to overwhelm you with quantum field theory that you're not prepared for. But here's what's frustrating. If you'd asked me a different kind of question, I could have helped you. If you'd asked, how do magnets repel? I could tell you about magnetic field lines, about domains in ferromagnetic materials, about how to calculate the force. If you'd asked, when do magnets repel? I could tell you, when like poles face each other. If you'd asked, what determines the strength of the repulsion? I could tell you about magnetic moments and distances and field strengths. If you'd asked, how can I demonstrate magnetic repulsion? I could describe experiments you could do with bar magnets and iron filings. All of those questions I can answer usefully, in ways that would increase your understanding and let you work with magnets. But why is different. Why is asking for a deeper level of explanation, and at some point you reach the level where there is no deeper explanation. Magnetism is pretty close to that level. It's one of the 4 fundamental forces. You can't explain it in terms of something simpler, because there isn't anything simpler. Let me tell you about my Aunt Minnie. Imagine I say, my Aunt Minnie is in the hospital. You ask, why? I say, because she slipped on the ice and broke her hip. Are you satisfied? Probably. Now imagine I say, my Aunt Minnie is in the hospital because of an instability in the interatomic forces within the crystalline structure of the ice beneath her feet. That's also true. The slipperiness of ice is because of the molecular structure of ice crystals. The breaking of her hip is because of the failure of bone material under stress. But you'd think I was crazy if I explained it that way. Because when you ask why is Aunt Minnie in the hospital, you're not asking for a physics explanation. You're asking for a human-level explanation. You want to know, did she have an accident? Is she sick? Did something unusual happen? The level of explanation you want depends on the context, on what you're trying to understand. When you ask, why do magnets repel, you want an everyday level explanation, something in terms of familiar concepts. But magnetism doesn't have an everyday level explanation. It's not like anything you're familiar with. It's fundamental. So I could give you the physics explanation, virtual photons, quantum field theory, gauge symmetry, but that's like explaining Aunt Minnie's hospital visit in terms of interatomic forces. It's true, but it's not the kind of explanation you were looking for. The problem is, for magnetism, there isn't the kind of explanation you were looking for. The physics explanation is all there is. Here's what scientists actually do when we encounter something new. We don't start by asking why. We start by asking what. What happens? Under what conditions? How much? How often? We observe. We measure. We look for patterns. Then we create models, mathematical descriptions that capture the patterns we observe. We test those models, make predictions, see if they're right. If they're right, we have a useful model. If they're wrong, we refine the model. At no point in this process do we need to answer why in the deep philosophical sense. We need to know how things work, how to predict them, how to control them. But we don't need to know why nature chose these rules instead of other rules. Take Newton's law of gravitation. F equals gmm divided by r squared. Why does gravity follow an inverse square law? Why not inverse cube? Why not something else? We don't know. We just observe that it does. Later, Einstein came along and gave a deeper explanation. Gravity isn't a force. It's the curvature of space-time caused by mass and energy. That's deeper than Newton. It explains more things. It makes different predictions that turn out to be right. But does it answer why? Does it tell us why mass curves space-time? No. It just gives us a different mathematical description that's more fundamental and more accurate. You could keep asking, why does mass curve space-time? And we don't have an answer. That's just how space-time behaves. Maybe someday we'll have an even deeper theory, string theory, maybe. Loop quantum gravity, something that explains Einstein's equations in terms of something more fundamental. But that theory will still have fundamental assumptions, and you could still ask why about those assumptions. You never escape this. At some point, you reach the bottom, the fundamental laws of nature, and you can't explain those in terms of anything simpler. They're just how reality works. Let me clarify something. There are different kinds of why questions, and some are answerable. Why explanation? Why is the sky blue? This asks for a mechanism, and we can answer it. Rayleigh scattering, wavelength dependence, atmospheric composition. Why purpose? Why do birds migrate? This asks for a function or goal, and we can answer it. Better food sources, breeding grounds, survival advantage. Why cause? Why did the bridge collapse? This asks for approximate cause, and we can usually answer it. Structural failure, material fatigue, design flaw. These are all legitimate why questions, and science can answer them. But there's another kind of why. Why fundamental? Why do electrons have the charge they have? Why is the speed of light 299,792,458 meters per second? Why are there 4 fundamental forces? These ask for explanations of the fundamental structure of reality, and we can't answer them, at least not yet. We can measure these things. We can incorporate them into our theories. We can predict based on them. But we don't know why nature chose these particular values and structures instead of others. Maybe there's a deeper reason. Maybe there's a theory of everything that explains why all the fundamental constants have the values they do. Maybe there's a multiverse, and the constants are different in different universes. And we're in this one because these values allow for complexity and life. Or maybe there's no deeper reason. Maybe the fundamental structure of reality is just brute fact. We don't know. When the BBC interviewer asked, "Why do magnets repel?" he was asking a why fundamental question, even though he didn't realize it. He thought he was asking a why explanation question, like, why does ice melt? Answer, heat breaks the hydrogen bonds. But magnetic repulsion is fundamental. It's not reducible to simpler phenomena in the way ice melting is, so there's no answer of the kind he wanted. Here's what I've learned after a lifetime in physics. You have to be comfortable with mystery, not ignorance, not giving up, but recognizing that at the deepest level, nature is what it is. We can describe it, we can predict it, we can work with it, but we can't always explain why it's that way instead of some other way. And that's okay. In fact, it's more than okay. It's what makes science interesting. If we could explain everything in terms of everyday concepts, there'd be nothing surprising about nature. It would all be obvious. But nature is surprising. It's weird. It's counterintuitive. Quantum mechanics is bizarre. General relativity is mind-bending. The strong force is nothing like everyday experience. These things don't make sense in terms of pushing and pulling and familiar macroscopic phenomena. They're fundamentally different, and that's what makes them profound. The mystery isn't a failure of science. The mystery is what we're investigating. Our job as scientists isn't to make everything feel comfortable and familiar. Our job is to describe reality as accurately as possible. And if reality is strange, if it doesn't match your everyday intuitions, well, that's just how reality is. You can reject it. You can insist that there must be a more familiar explanation. Or you can accept it. You can learn the mathematics. You can work with the strangeness. You can let go of your demand that everything be reducible to things you already understand. The second path is harder, but it's the path to actual understanding. I remember when I first learned quantum mechanics. It made no sense. Particles being in two places at once, wave functions collapsing when you look, uncertainty as fundamental rather than just ignorance. It all seemed impossible. But I kept working with it. I learned the mathematics. I did the calculations. I compared the predictions to experiments. And eventually, I stopped trying to make it make intuitive sense. I just accepted this is how nature works at small scales. Did I understand it in the sense of having a comfortable mental picture? No. But I understood it in the sense of being able to work with it, calculate with it, predict with it. And that's enough. That's what understanding means at the fundamental level. Not comfort, not familiarity, but being able to work with reality as it actually is. The same is true for magnetism, for gravity, for all the fundamental forces. You can learn the mathematics, you can make predictions, you can build technology, but at some point you have to accept this is just how nature works. There's no deeper why that I can give you. And once you accept that, once you stop demanding that nature make intuitive sense, you're free to actually learn about it. You're not constantly frustrated that it doesn't match your expectations. You're curious about what it actually is, not disappointed that it's not what you thought it should be. So if we can't answer why, at the fundamental level, what can we know? We can know how things work. We can describe the mechanisms. We can write down the equations. We can know when things happen, under what conditions, with what probability. We can know what the consequences are. If you do this, that will happen. We can make predictions and test them and refine our understanding based on the results. This is enormously powerful. This is how we've built the modern world. Computers work because we understand quantum mechanics well enough to design transistors, even though we don't know why electrons have the properties they do. We know that electrons tunnel through thin barriers. We know the probability of tunneling. We can calculate it. We can design semiconductor junctions that exploit this effect. Do we know why tunneling happens? Not in the sense of reducing it to more familiar phenomena. It's a quantum mechanical effect. It just is. But knowing how it works is enough. We've built the entire information age on that knowledge. GPS works because we understand general relativity well enough to correct for time dilation, even though we don't know why mass curves space-time. We know that clocks run faster in weaker gravitational fields. We know by exactly how much. We can calculate the correction needed. Do we know why gravity affects time? Einstein's equations describe it mathematically. But why space-time has this structure? We don't know. But knowing how it works is enough. Your GPS wouldn't function without these corrections. The practical application doesn't require philosophical understanding. Medicine works because we understand biochemistry well enough to design drugs, even though we don't know why the fundamental forces have the strengths they do. We know that certain molecules bind to certain receptors. We know the binding energies. We can predict which drugs will be effective. Do we know why electromagnetic interactions have the strength they do? Why the fine structure constant is 1/137? No. But we can measure it, use it, build on it. Understanding how things work is enough. We don't need to know why they work at the deepest level. The how is sufficient for prediction and control. And that's what matters for practical purposes. Let me give you another example. Superconductivity. Below a certain temperature, some materials have exactly zero electrical resistance. Current flows without any energy loss. Why? The full explanation involves quantum mechanics, phonon interactions, Cooper pairs, and energy gaps. But even that explanation doesn't tell you why nature allows this phenomenon. It just describes the mechanism. Yet we've built MRI machines, particle accelerators, and quantum computers using superconductivity. We don't need to know why nature allows zero resistance. We just need to know how to achieve it and how to use it. The why is philosophical. It's about satisfying curiosity, about feeling like the universe makes sense. And there's nothing wrong with wanting that. I want it too. But I've learned that at some point, you have to accept. This is just how nature is. We observe it, we measure it, we describe it mathematically, and that's enough. So when the BBC interviewer asked me, why do magnets repel? What should I have said? I could have given him the quantum field theory explanation. Virtual photons, momentum exchange, gauge symmetry. But he wouldn't have understood it, not because he's not smart, but because he doesn't have the background. I could have given him a simpler answer. Magnetic fields create forces, but that's just restating the question. I could have lied, made up something that sounds good but isn't true. The magnetic field lines push against each other, but I'm not going to lie. That's not what I do. So I told him the truth. I can't explain it in terms you'll accept, because any explanation I give will either be too technical to understand, or too shallow to really explain anything, or just plain wrong. The honest answer is, magnetism is fundamental. It's one of the basic forces of nature. We can describe it mathematically. We can predict its effects. We can use it in technology. But we can't reduce it to more familiar phenomena, because there are no more familiar phenomena for it to reduce to. It's not like anything else. It's itself, and you have to accept that, not because I'm being difficult, not because I'm hiding something, but because that's the nature of fundamental reality. At some point, the explanations end. You reach bedrock, and all you can say is, this is how nature behaves. Why? Is the most dangerous question in science. Not because it's wrong to ask, not because we shouldn't be curious, but because it's often asking for something that doesn't exist. An explanation in terms of more familiar concepts, a reduction to everyday experience. And for fundamental phenomena, that's impossible. You can keep asking, why? Forever. Each answer generates a new why. You never reach a final answer that satisfies the questioner completely, unless you accept. At some level, nature is just what it is. We describe it, we measure it, we work with it, we make predictions, but we don't always know why it's that way instead of some other way, and that's okay. That's not a failure of science. That's the nature of reality. The universe doesn't owe us an intuitive explanation. It doesn't have to make sense in terms of our everyday experience. It just has to be consistent and observable and describable, and it is. So the next time someone asks you why about something fundamental, remember, the question might be impossible to answer, not because we don't know enough, but because the question itself is asking for something that doesn't exist. The honest answer is sometimes, that's just how nature is. And if that doesn't satisfy you, well, welcome to physics. We're all unsatisfied here. That's what keeps us working. The mystery isn't a bug, it's a feature, and it's what makes the universe endlessly fascinating.